Mechanical systems are often subjected to vibrational loads. When this occurs, the vibration travels through the parts in the model and cause them to deform, depending on the first vibration frequency. The part in the mechanical system oscillate in different ways, creating different mode shapes. Each mode shape causes the parts to deform in a specified way. Each mode shape corresponds to a resonant mode, which is a frequency that causes the part to the oscillate more instantly. Each resonant frequency depends on the part geometry as well as the stiffness of the material. Mechanical systems undergo vibrational load due to being excited by the objects such as motors, waves, and dynamic load cases. These objects cause the vibration and transfer them through the mechanical system. When the vibrations are transferred, the parts feel different resonant frequencies depending on how they are connected together. When connectors are included in the system, it cannot be treated as a perfectly stiff. This changes the natural frequencies of the system, making it important to study how changing connections affect the results. In this tutorial, I will analyze the frame that support our engine to find its resonant frequencies. Two different local interactions will be used on the frame, and the resonant frequency will be compared to the determine which interaction creates a softer mechanical system. In this model, the lower frame supports a heavy engine. I want to analyze the frame to determine if there are any natural resonant frequencies which could be excited by the vibration from the motor. However, before I begin the frequency analysis, I want to mention a couple assumptions which will be made with regards to the analysis. For the first assumption, the engine can be treated as a remote mesh in this model. Since the support frame is to focus of the frequency analysis, this will decrease the simulation model size with accurate representation of the global system. Secondly, I want to point out that some of the intermediate components that connect the engine to the frame are missing. These components are assumed to be very stiff and light in the comparison to the engine mass, which means they can be suppressed in the analysis. Now that I have started the assumption about the model, I'll begin walking through the first frequency analysis. Much of the simulation study has been prepared ahead of time. To access it, I'll navigate to the simulation study tab. Frequency all bounded at the bottom of the interface. This study consists of all of the frame components having bonding interactions added between them. This means that all of the components are treated as being perfectly connected and the components cannot separate from one another. You can see these interactions if I expand the local interaction in the simulation tree. This graphically displays the faces of the component that are treated as bonded together. To begin setting up the frequency analysis, I'll set the engine as a remote mesh. To do this, I'll expand parts in this tree. Then right click on the engine, tilt it, engine 1, and choose it treat as a remote mesh in the menu. To automatically select the engine as the remote mesh. And the second group box, I'll choose the four faces of the frame that support the engine. This means I simply need to select all your cylindrical faces on the top frame. When I click to green check, you can see the remote mesh added in the simulation tree. Next, I'll add fixture to the model. I'll fix both of the yellow and white frame pieces at the bottom. I'll right click on the fixture in the tree. Select fixed geometry. Choose the two endo faces on the left. Then the two end faces of the right. And click the green check. The next step would be mesh to the assembly. However, before I do this, I want to verify a couple of properties for the simulation study. I'll right click on the study at the top of the simulation tree and choose properties from the list. In this study, I would want to analyze the first four resonant frequency. So I'll make sure the number of frequencies is set to 4. The solver type is not particularly important for this problem. So I'll make sure the solver selection is set to. Now the mesh can be applied to the assembly. I'll right click on the mesh and select create mesh. I'll enable the curvature based mesh parameter, and in the mesh quality tab I'll make sure all parts selected are specified as draft mesh quality. When I click the green check, the mesh is generated for the assembly. Now you can run the analysis. I click on the run this study button in the command manager, and the solver produces result for the first 4 resonant frequency in the model. This resonant frequency for each model is listed in the upper left corner. To list all of the resonant frequencies found in the model, I can right click on the results folder in the tree and select list resonant frequency. In this table, each model number is listed with the corresponding frequency, which is shown in Hertz in the second column. The first made has a resonant frequency of 127 Hertz, while the second made has a resonant frequency fairly close to this value. This means that the frequency range has a large potential to cause deformation in the bracing. Since the first two mates are so close to each other, I'll close out of this box for now. Each mode can be animated to show the shape or a particular resonant frequency. To animate the model, simply right click on the model into the results folder and select animate. At first, the model calculates frames in order to display the animation, and then the animation is shown and continues to loop. In the property manager, there are controls that can be adjusted. I'll stop the animation for now. Increase the number of frames 10 to give a smoother animation, and changes the speed to around 80. Now when I play the animation, all 10 frames are created and the animation plays back. This can be done for any of the four modes in the result. I want to point out that this animation is not displaying the actual displacement of the parts in the model due to the resonant frequency. It is simply exaggerated representation of the deformation trends in the model. In next video, I'll perform the same study on the assembly. However, the bonded interaction will be adjusted, and some of the interactions will be, then I'll compare the resonant frequency of the two studies to see which model is softer. Now that the resonant frequency have been found over the model using bonded interactions, if I find the resonant frequency for the model utilizing the free interaction type, I'll switch over to the study tab frequency bonded and free at the bottom. And when I expand the local interaction item in the tree, there are 3 free interactions established. The first occurs between 4 members at the bottom of the frame. The second occurs between the 2 bars and the member just below them. And the third interaction occurs between the bars and the orange mounting frame above them. Because of these conditions, number of pin connectors were added to the study, which you can see when I expand the connection items in the tree. The first step in the study to add fixture to the members to the bottom, as I did in the last example. I right click on the fixture in the tree, enable the fix geometry tool, select the same 4 faces as before, and click to green check. Next, I'll add the mesh to the assembly by right click on the mesh table in the tree and selecting create mesh. I'll use the same parameters as I last study, including using the curvature based mesh parameter as well as a specifying draft mesh quality, and click the green check. Before I run the analysis, I'll adjust the properties of the study. I'll change the study to find 4 frequencies and make sure the solver selection is set to automatic. Now you can run the analysis. I'll click Run Study in the Command Manager. And the four modes appear in the results. In order to determine which assembly has a softer interaction, I want to compare the resonant frequency of these four modes to the previous example. I'll right click on the results folder in the tree and click the list resonant frequencies. You can see here that the first two modes have resonant frequencies at 90 Hz and 100 Hz. To compare the results with the previous study, I can click the compare tool in the simulation command manager, and I'll select the option all studies in this configuration to compare different studies. And then I'll click check the boxes for the first two resonant frequencies of both studies. When I click the green check, the mode shapes are compared for each resonant frequency. The first mode shape is shown at the top of for each model, and the second mode shape is shown on the bottom. The first study has a resonant frequency at 127 Hz and 130 Hz, while the second study with the free contact conditions had resonant frequency of 90 and 100. This means the second study has a softener build and it more accurately represents reality. The study can have the each result saved to e-drawings, which is useful for sharing results with other designers or employees collaborating on the project. Simply click on the plot tools and drop down the command manager. Then select save as. In the dialog box, make sure that the file type is set to e-drawings and give it a name. And when I skip ahead to show the file open in e-drawing, you can see the first mode shape displayed with the stress plot and alongside the model.